What's up, my little cornbread muffins? Today, today we're gonna finish up a unit that we probably should have done a unit ago, but we're gonna talk about motion, specifically simple harmonic motion. And this is, I don't know if I think this is interesting or not. It's all right. You know what I mean? It's not up there with momentum. It's not up there with a lot of my other favorite topics. You know what I mean? But it's all right. It's kind of cool. So we'll talk about what it is, how we measure it, when it happens, who it happens to, what time of the year it is, and what happens if you see a wild harmonic oscillator in the wild. So without further ado, let's talk about your vocabulary. So a simple harmonic motion. English is tough, you guys. Simple harmonic motion occurs when there is a restoring force, meaning a force that's trying to push something back to where it started. It's trying to restore the original position to the object. So restoring forces can result in oscillatory motion. When a linear restoring force is exerted on an object displaced from an equilibrium position, the object will undergo a special type of motion called simple harmonic motion. So basically, there's a few important words here. We need a linear restoring force, meaning the force needs to equal some constant times however far it is from the equilibrium position, right? And this is already looking eerily similar to something else. And the force needs to be in the opposite direction of the displacement. Bizarre. It's almost as if we have an equation that is exactly this. This is our spring force. This is Hooke's law, right? So springs are one way we can get things to bounce back and forth. There is another very common one that we're going to look at. But the idea is we need a force that gets stronger the farther you are from where you started, and it has to push you back towards the direction you came from. If this force is exerted on an object and it's displaced from equilibrium, it will undergo a special type of motion called simple harmonic motion. Simple meaning it's not all that fancy. It just goes out and comes back. Harmonic meaning it's gonna repeat itself. Okay. And we've seen repeated motion before. Things going in circles have repeated motion, right? It just goes around and around and around. We're not talking about continuously going in one direction, though. We're talking about it's going to go out, it's going to come back, it's going to go the other way, it'll come back again, it'll go back out, it'll come back in, it'll go back out again, and so on forever. Almost forever. But that's simple harmonic motion. The period is the time that it takes for a simple harmonic oscillator, I'm going to abbreviate that SHO from now on, to move to the other side of its oscillation and come back. So if we're talking like a pendulum, which is a great harmonic oscillator, we're talking for this thing to swing all the way over here and then all the way back to where it started. The full travel there and back, the time that takes is the period of oscillation. There is another kind of time-dependent word that we need to know, and that's frequency. And frequency is like measuring the other part of period. Period measures how long it takes to do one thing. Frequency is the number of things that happen in one amount of time. So this is time per thing. This is things per time. Does that make sense? So they're actually reciprocals of each other, but we'll get to that in a couple of slides. So let's look at our two simple harmonic oscillators. The first type of harmonic oscillator is a pendulum. Oh, come on. pendulum. And this is exactly what you think it is. Maybe not quite as interesting. You might be thinking of Newton's cradle, which is like this, right? And it's got a whole bunch of little pendulums, and you like pull this one, and then you let it go, and then the one on this end goes up. This thing's kind of like a pendulum. This thing's cool, but we're thinking like if you just took one of them, the boring version of Newton's cradle. So it's just a thing, a mass on the end of a string, and it just boop, 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 back and forth, and that's all it do. So that's our first type of simple harmonic oscillator. It goes out, it comes back, it goes out again. The second type is, I don't think this has a nice name for it. It's not a pendulum, but it's just a mass on a spring. Hopefully this is frictionless. But if it's not, say la vie, you know what I mean. But it's got a mass of some known mass m and a spring here. You have to pull the mass out so that the spring is stretched, and then you let go, and then it does this back and forth. Right? If you don't displace it, if this is just its rest length and you leave your mass there, it's not going to do anything, right? If you pull it out and then let go, it's going to boop, 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 back and forth. You could push it in. You could push it in and then let it push it out. And it's going to push out and then come back in. So the idea here is we have a force that no matter what happens, it's always trying to push us back to the equilibrium position. The equilibrium position for a pendulum is just straight down. So if I pull this out, the force that's going to pull it back in is gravity, right? Gravity pulls down. Because this is at an angle, it's exerting a torque on this and is trying to rotate it back towards equilibrium. Once it gets here, it's moving and there's not a unbalanced force anymore. So because it's moving, it just keeps moving through the equilibrium. And then gravity says, hey, wait a minute, you went too far. And now gravity's pulling down. Now it's kind of torquing it this direction and it pulls it back to equilibrium, but it's cruising. And it goes, wait, hang on a second, you went too far again. And then it pulls it back and it pulls it back and it pulls it back. And then next thing you know, you're oscillating. Same thing here. You pull your mass out so that it's here. Then the spring is going to pull that way on it. It's going to be cruising in. It's at equilibrium. So the spring is not exerting a force because it's not pushing, it's not pulling, it's not stretched. So there's no Hooke's law. The distance is 0. But it's moving, so it just keeps on keeping on, and it slides through the equilibrium position and compresses the spring. The spring says, hey, watch it, buddy. You're getting a little close, and starts pushing it back out. And the farther in the box moves, the harder the spring presses. It'll stop. The spring will push it back out because now it's compressed. It'll pass this again, come back out here. This distance from equilibrium to here is known as amplitude of oscillation, but we're not going to trip too much about the amplitude. And here's why. It's because the period of these harmonic oscillators does not depend on the amplitude. Let's look at it. Our period, so the amount of time that it takes for this pendulum to swing all the way over and all the way back is 2 pi. And this is kind of a product of things doing things that repeat themselves. This is kind of like sines and cosines come up a little bit here. So we shouldn't be too surprised to see pi's, right? Anytime something is repeating itself in like a sine or cosine fashion, you generally get some pi's hanging out just because. But the important part here is this is a constant. So this is a number. This is like 6.28-ish, give or take. It's a constant. Oh, well. The important thing is the variables. So the time that it takes for our pendulum to swing and come back is proportional to the square root of L. And L is the length of this pendulum. And G is weight equals mg. It's that G. It's the strength of gravity. It's the gravitational field strength. It's the acceleration due to gravity. It's a constant that helps us determine how hard the Earth is pulling on something. So L's on top. If I make L longer, if I increase the numerator, this number goes up and our period increases. If I make L shorter, so it's only like a little guy, then the numerator goes down, the period goes down. There is another variable here, G. One way you can change G is you go to another planet. Okay, that's not very practical. Some other ways that you could increase G would be to, hold on, let me just not erase this. Let's lock this down for a second. Lock in place. There we go. One other way you could change G is you want to make something feel as if it's heavier. So how could we do that? If this pendulum were inside like a rocket ship, those are really bad flames. All right. And then this whole thing is accelerating up. Because you're accelerating up and you have the force of gravity pulling you down, this pendulum, if I were in a closed box and I couldn't see out and I didn't know I was in a rocket ship, it would feel like this thing is heavier than normal. If I were holding it on my lap, there's a rocket on, this thing's getting pressed down into my lap, and it feels heavier. So we can artificially increase G by accelerating up, or if we accelerate downwards, then it's not quite as if you're in free fall, you don't feel heavy. Is the best way I can explain it. So if you accelerate downwards, you're kind of artificially decreasing G. So it's what is this G force relative to your reference frame? But we're not going to trip about it too much in these notes. But just be aware, if you accelerate up, G will feel as if it is larger. And if you accelerate down, G will feel smaller. So we can sort of change G, but you've got to accelerate up and down, which means you got to move up and down. And we don't have a lot of really tall things to do that with. So it probably won't happen too often. Let's look at the period for this thing. So our mass here, it makes sense that if this thing is heavier, it would be harder for the spring to push it, right? So instead of having the length of our pendulum at the top, we have the mass of the thing on the end of the spring. The heavier this mass is, the less acceleration that this spring can give to it. So it increases the time it takes for the simple harmonic oscillator to oscillate back and forth. You might say, Mr. Brown, why doesn't this have a mass? If I make this heavier, shouldn't it take longer? You would think so, but the issue here is the force driving this thing is weight, and it has mass in it. So the heavier you make this thing, sure, you're moving more mass, but the thing moving the mass depends on the mass itself. So they kind of come out in the wash and cancel each other out. If I'm heavier, I'm harder to move. But if I'm heavier, gravity pulls on me harder, so it's moving me more. So it cancels out. Here, because our restoring force is not dependent on the mass of this object, it doesn't come out in the wash, and the mass resists being accelerated. The thing that will make this oscillate faster, if we increase the force, it will oscillate faster. So the way we increase the force of a spring is not necessarily by compressing it, we don't compress it. what we do alternatively is we put a stronger spring in. So K. So you want to think about it as the thing resisting will slow it down. So the mass, or if this is really long, then it kind of has like a long path to travel on. So the length will resist here. Conversely, the thing driving the system, if you increase the strength of the thing driving it, the spring or gravity, then it will oscillate faster. Okay. All right, so there's our formulas for the period of simple harmonic motion, and that's really what you're going to be tested on, is how long does this thing take to go back and forth. Okay. Let's talk about frequency briefly, and then we'll dive into some problems. So frequency is the reciprocal of period. Literally, period equals 1 over the frequency, or vice versa. The frequency equals 1 over the period. They are quite literally reciprocals of each other. Okay. Again, period is how long it takes to do one full rotation. Frequency is one rotation or one oscillation per unit of time. So this is how many times does the thing happen in a given amount of time. This is how much time does it take for one thing to happen. Slightly different, but it's important enough that they gave it a name. So frequency, because it is the reciprocal of period, and period is a time measured in seconds. If we do the 1 over this, frequency is measured in 1 over seconds or per seconds. It has its own name. It's a hertz, Hertz. It's named after a guy. But a 1 over seconds or a per second is a hertz or a hertz. A single hertz. I don't know if it's singular because hertz with a Z is the guy's name. But I feel like hertz sounds plural. I'm not an English teacher. Anyway, so to get the equation for the frequency, what we do is we take our equation for our period, L over G, and we flip this whole thing. So we flip the 2 pi, it's 1 over 2 pi. We flip the fraction inside the radical, it's G over L now. Same thing here with the frequency for a spring oscillator. Same deal. It's the same period equation flipped, and here you go. I'm giving you these so that if you want them, you can write them down. I don't have these memorized. I remember these, and then I flip them when necessary. So, you know what I mean? I've got limited storage space in my brain. It's not worth the effort to memorize this too, unless you're into memorizing things. But there you go. So there's the frequency in case you need to use it. We're not going to focus on this too much, but it comes up in your homework. Okay, so let's talk about the period of the pendulum, and then we'll get you on your way. So a pendulum is oscillating back and forth with some period t0. So it takes some amount of time. We don't know how long. Well, we do know how long. It's whatever number this is. Could be 10, could be 1,000, could be whatever we want. A student notices that slightly less than 2 seconds and wants to increase it to 2 seconds. So they notice this is less than 2 seconds and they want to increase it. The student wants to increase the length. I don't know that I proofread this very well. They want to increase the period from slightly less than 2 seconds to 2 seconds. They need to increase something. They need to change something about the system to do that. And their options, their ideas are, they want to increase the length of the string the bob is on. Okay, so they want to make this longer. They want to increase the mass of the bob. They want to make the bob bigger. Or they want to increase the initial angular displacement of the bob. They want to take this thing and pull it farther to the side. which method could work for the student? Okay, so let's start with our formula and go from there. The period of a pendulum, a mass-driven pendulum, is t equals 2 pi times the square root of L over G. Okay, so I want this quantity to increase. 2 pi is a constant, so we're going to just straight up ignore that. It's a number. It'll come out in the wash. I can't adjust pi. I cannot physically alter the ratio of a circle's radius to its circumference. I wish I could, but I can't. It's a theoretical constant, right? So the only options we have to adjust the period of our oscillator is the length or the strength of gravity. So if I want to increase the period, I could increase the numerator. If I make the top bigger, the whole number goes up. So we could increase the length of the pendulum. That's one of the options. They want to increase the length of the string the bob is on. So check mark, that would work. Increase L. It's French now. Increase L, check mark. That could work. Let's investigate the rest of these. Increase the mass of the bob. Like we said on this slide, the mass doesn't really affect the period. Not really. I'm being a little wishy-washy here. It absolutely has zero effect on the period of a pendulum because the force driving the system also increases with mass, and making something heavier doesn't work if making it heavier makes the force stronger too. So the mass is not going to affect the period of this pendulum. It would affect the period of a mass on a spring because the driving force is not due to gravity. So this would work if we were looking at something with a spring here. But because it's a string and not a spring, the mass, that's not going to work. Let's talk about this initial angular displacement of the bob. What happens if I pull this thing farther to the side? It seems like this should increase the period because if I pull it farther, let's look here. This one has an angular displacement of whatever that is. This one has an angular displacement of whatever this is. If it has to go farther, it makes sense that it should take more time. However, this is not the case. Increase theta does not work. The reason for this is because as I pull this farther over, let's imagine a bob out here. And let's consider the torque being exerted on this thing by gravity. Torque is equal to the force twisting the system, which is the weight, times the distance from the axis of rotation, in this case L, times sine of theta, which is theta is the angle between where the force is being applied and R. So here it's 90. As this thing swings down, the weight's down here, and then we're looking at this huge angle. And as it comes to the bottom, this angle is eventually 180 degrees. So sine of 90 is 1. Sine of 180 is 0. So as this twists around, we get less and less and less torque on the system. So increasing the angle also increases the torque, which means this thing is being turned back towards where it came from harder the farther you move it. So very similar to the way that mass comes out in the wash, because the driving force, the bigger the driving force, the bigger the mass, the bigger the weight, the bigger the angle, the bigger the torque. So it kind of comes out. The second caveat, and I'm going to feel bad if I don't tell you about this, is this, let's try one more time. This formula is a lie. It's not a light. It's a asterisk. This formula is only good. I spell good for small thetas. When they come up with this formula, when the proverbial they come up with this formula, they do an approximation that you should be aware of. They kind of look at this torque, and at some point they say sine theta equals theta. Okay, let me say that again. The sine of the angle is equal to whatever the angle is. And this is almost true when theta is less than about 15 degrees. I think that's where most university teachers say, you know what, after that, it's a little, then it's not quite the same problem anymore. So this is only really good if we don't pull this too far to the side. If you pull it too far to the side, it actually does kind of a little bit depend on theta, and I think bigger theta does make the period longer. But in this class, you see how theta is not in this equation? Then it doesn't matter. So the only options in this class for changing theta are make the thing longer, or sorry, not theta, but the period is make your string longer or shorter, or change gravity, or artificially change gravity by accelerating up or down. So of the three proposed options, increase the length of the string, that'll work because L is in this formula. Increase the mass? Nah. If you increase the mass, you increase the restoring force and they cancel out. Pull it farther to the side? That's against the rules. Don't do that. You're going to goof up the formula. And hand waving, theta's not in this formula, so who gives a hoot? It doesn't affect it. So there we go. So we can only increase the length to make it take longer, so it's got that desired period of 2 seconds. Okay. Let's talk about the energy of these things. So I could ask you, how could we change the period of this? But we've already done that problem. You just look at the formula and, adjust. So we could say T equals 2 pi m over, sorry, not square root. There we go. Square root m over k. So if I want to make the period of this longer, we could either increase the mass of this block or we could decrease k. If you make the bottom smaller, then you're cutting up into more pieces and you get a bigger final answer. So you can either make this heavier or make the spring weaker and softer. There we go. We did the problem. Okay. Whoops. Let's erase more carefully this time. Okay. So let's read the question. A mass of 0.25 kilograms is attached to a spring with a spring constant of 81 newtons per meter. The mass is pulled 0.3 meters to the side and then released. The mass begins to oscillate back and forth in simple harmonic motion. What position in the oscillation has the maximum potential energy, the maximum kinetic energy, and the maximum mechanical energy? And where is the largest acceleration during the oscillation going to be found? So we want to look at a couple of things. Let's make some graphs. We want to look at our potential energy of a spring as a function of maybe position. Where is the thing going to be the biggest? Where is our kinetic energy going to be the biggest? Where is our mechanical energy going to be the biggest? And then where is our acceleration going to be the biggest? Okay. So let's make some graphs. So let's start by defining some spots, right? Here's x equals 0.3. This is our maximum displacement. And then it will come back here to x equals negative 0.3 meters. And this will be its maximum displacement in the other direction. So we'll say here is negative x. Here is positive x. And then here's x equilibrium. And we'll do the same thing here. Negative x, positive x, equilibrium. Negative x, positive x, equilibrium, then same thing here. Okay, so let's consider our mass out here. The potential energy due to having a spring, the formula for that is 1/2 kx squared. So the farther we are, the more potential energy we have. So at equilibrium, x is 0, and we have no potential energy. Okay. If I displace to the right, it increases, and as it increases, x is squared. So this is going to be kind of parabolic, like so. And if we go negative, notice how your if we square a negative, it turns positive. So this will also increase, and we're going to have kind of a parabola looking potential energy. So our maximum is in two places. It's at x equals 0.3 meters and x equals negative 0.3 meters. Both of them will be approximately the same height because it doesn't matter which way we displace it. As long as it's not at the equilibrium position, we've stored some energy in the spring and we have potential energy. Okay. Then the spring will pull or push really hard on these boxes, trying to get them to go back to the equilibrium position. Okay. When it's at the equilibrium position, the force of our spring is equal to negative kx. X is 0 at equilibrium, so there's no force, but because it's being pulled so hard, it's zooming towards the center, towards equilibrium, and it's going to be booking it. As soon as this box comes past and is a little bit past the equilibrium position, then the spring is going to start pulling back and slowing it down. So what's going to happen is it's going to stop here at the end. It's going to speed up here. It'll start slowing down once it passes equilibrium position and stop again. So we get kind of the inverse graph here for our kinetic energy. It's stopped at the ends and it's going really fast in the middle. If this system is a closed system, so we include the spring and the mass in our system, there's no friction, the total amount of energy, well, as this decreases, we're converting it into this. And after we pass equilibrium, we convert our kinetic energy back into potential energy. Our total mechanical energy for the system will be conserved, and it will be a constant amount. Okay. The last thing we need to talk about is the acceleration of this mass. So when it's out here, it's going to accelerate that way because our unbalanced force, this spring, is going to be pulling towards equilibrium. When this is here, it's going to be pushing that way. So let's say that our usual, that direction is positive. When it's way out here, our acceleration is going to be really big because it's going to have a big stretch, a big spring force, pulling it in the negative direction. It's going to have a big negative value. When it passes equilibrium, the spring isn't stretched, so there's no force. It's just moving because it was already moving. So force is 0, which means acceleration is 0. And back here, the spring is going to be pushing it that way in the positive direction, just as hard as it did over here, because they have the same displacement. So our acceleration graph is going to look something like this. So our maximum acceleration, well, if we're going positive, negative, it's right here. If we're talking about just magnitude, because it's the farthest from equilibrium and the spring force is at a maximum, and we look at just the absolute value, it could be at either of the endpoints. When it's farthest from equilibrium, that's when our spring is pulling or pushing the hardest. So we have the most unbalanced force and the biggest acceleration. Okay, cool. That's a cool problem. All right, last thing we need to talk about. What if it's both? Por qué no los dos? So we have a mass suspended from a spring such that it hangs vertically at rest at its equilibrium position. So this thing is hooked onto a spring and then just dangles there. The mass is 2 kilograms. The spring constant is 100 newtons per meter. And the length of the spring when the mass is hanging from its motionless, this doesn't sound like good English either, is hanging and is motionless is 0.8 meters. Then the mass is lifted. So right here, this distance, this is 0.8 meters. Then they're going to lift the mass up so that it's maybe here. And then this distance is 0.6 meters. And then it's released. So this spring is going to stretch. It's going to come down here. Boing. And this is going to stretch. Well, I went back 0.2. So I'll probably go out 0.2 as well to 1.0 meters. It's going to stretch to 1 meter and then it'll bounce back up and it'll bounce back down. And it'll bounce back up and it'll bounce back down. And I've drawn this a little inaccurately. It should be right in the middle, but you'll forgive me. The mass then bobs up and down in simple harmonic motion. What is the period of oscillation? Mr. Barton, do we need to combine the equations somehow? No, we don't. This is a question that I think is meant to trick you by making it both and making you think that the mass is somehow more complicated than it really is. Yes, it is going up and down because gravity pulls it down. But there is a nice result that you can get if you want to go through a bunch of dense algebra and physics and stuff. True. If I took this and I rotated it like this equilibrium position is definitely not going to be 0.8, right? Gravity stretches this spring until F equals kx equals the weight. And then it's at equilibrium and doesn't accelerate. This has to be stretched already for it to be at this equilibrium position. The good news is all this does is change our equilibrium position from maybe this was like 0.4 meters is its unstretched length. And then stretched because of gravity because it's hanging is 0.8. It doesn't change really anything else about the problem besides where the equilibrium is. So if we see this is going up and down, not because we're tilting it and then gravity's pulling it back. It's going up and down because our spring is being stretched and then compressed, and then stretched and then compressed. So because the spring is the thing pulling this mass up and down, up and down, up and down, it's the restoring force, and we should use the period of a spring, not the period of a pendulum. So it's square root of m over k. The mass of our object is 2 kilograms. So we have TS equals 2 pi times the square root of 2 over. The spring constant is 100. Okay. The square root of 100 is 10. So the spring period is 2 pi square root of 2 over 10. And then the 2 and the 10 can reduce to 1/5. So the period of our spring is square root 2 over 5 times pi seconds. And then you could throw that in a calculator and get a number. But do not get confused. Just because it's hanging does not mean it's a pendulum. Hanging does not a pendulum make. Oscillating sideways is a pendulum. Because it's going up and down, the spring is the thing doing all the heavy lifting here. So we use the springs period. And there you go. There you have it. That's a simple harmonic motion. If I asked you frequency questions about all these, you could just solve for period, get this, and then reciprocal. Do 1 divided by whatever number this is, and then that would be your frequency. It's not that bad. That's why I'm not doing an example on it, because really it's, if you can solve this, then you can do a reciprocal, I hope. But there you go. So if you have any questions, be sure to let me know. If you feel like you were taught super well, maybe consider digging down into your pockets, reach down under the lint, under your wallet, under your keys, and pull out one of those likes for this YouTube video. Just leave it in the charity jar down below the video. It's really easy. You just click the little up arrow, or is it a thumb? I don't know. Maybe I've been on the wrong website too long. But do whatever it is you do on YouTube. Increase those engagement numbers. And I'll catch you guys next time. Have a great day.